This is Physics 2211 Lab 3 Black Hole. The purpose of this lab is to determine the mass of a black hole by observing an orbiting star and then using that found mass to determine the initial speed of a spaceship so that it can leave the surface of a planet and fly around the black hole. The results we get from this lab are the mass of the black hole, which is 1.73 times 10 to the 34th kilograms, and the initial speed of the spaceship, which is -4 times 10 to the 7th meters per second in the x direction, and 3.5 times 10 to the 6th in the y direction. The methods used for this lab are GlowScript and Excel. GlowScript was used to computationally iterate in order to determine the mass of the black hole, as well as predict the motion of the spaceship, and Excel, which was just used to average the mass of the black hole. The principles used in this lab are Newton's second law, which is the momentum principle, and this states that the net force experienced by a system is equal to the system's change in momentum over the change in time. From this, we derive the position update formula as well as the velocity update formula, which we'll be using within the code. And our other principle we use is the force of gravitation, which is F equals the universal gravitational constant g times both masses over the distance between them squared. So part 1 of this lab is finding the mass of the black hole. So we set our initial conditions, which is the mass of the star, and then make sure we have that gravitational constant in there. We edit our delta t to be equal to 1 Earth day. Then we edit our momentum initial and momentum final, according to the definition of momentum, which is P equals mv. And finally, we edit delta v and delta p, just going off that change is equal to final minus initial. Next, we define dp dt, which is F net according to the momentum principle. Then we define p hat and dp dt parallel. P hat is the direction of the momentum, and this can be found by dividing the initial momentum by its magnitude. And dp dt parallel is the magnitude of dp dt times p hat. To find dp dt perpendicular, we can use the equation dp dt is equal to the sum of both the parallel component and the perpendicular component, and just rearrange that. And finally, we calculate the mass of the black hole, and we get a value of 1.73 times 10 to the 34th kilograms. Again, here's our mass of the black hole. Here's our F net parallel, and F net perpendicular. Some possible sources of error for this part of the experiment would be averaging the mass of the black hole may have led to an inaccurate final value. So for part 2 of this experiment, we're going to use the mass of the black hole that we found in part 1, and we are going to guess and check for our initial speed. So we know we cannot move faster than the speed of light, but if you move too slow, you risk crashing into the planet or getting sucked into the black hole. So through guess and check, I got values of -4 times 10 to the 7th meters per second in the x direction, 3.5 times 10 to the 6th in the y direction. And just to be clear, our system is the spaceship, and our surroundings is the planet and black hole. So we need to find the net force on the planet, which will be equal to the force due to the black hole plus the force due to the ship. Then we find the net force on the ship, which is the force due to the planet and the force due to the black hole. And then we will use the velocity update to then update position for both the planet and the ship. So as a result, again, here is our initial velocity of the spaceship. And possible sources of error is that I didn't let the code run for long enough, and the mass of the black hole may be inaccurate due to averaging the values. Although the momentum principle states that F net and dp dt are the same, there is a difference in the way that we find these values. And that is that F net requires knowing the mass, which we did not have in part 1 since we were finding the mass of the black hole, and the rate of change of momentum can be found using the object's motion over time with its time. As stated at the beginning, according to the momentum principle, the two quantities are equal. So what if instead of just trying to fly past the black hole, we're actually trying to orbit it, and what initial velocity would be needed? So I was not able to successfully get the ship to orbit the black hole, but I do know that a lesser speed would be needed so that the ship doesn't have as much momentum, and that gravitation coming from the black hole can pull it in and keep it in orbit.